Right, good evening. This is the final session on the required practicals for paper 2. So we're going through, I think there's 5. One of them is for separates, all the rest are for everybody, basically. But there's one on acceleration, reflection, can't remember the waves and things like that. So it's, again, I've got these PowerPoints where it kind of goes over the practical and they ask certain questions and the red is the answer. These are typical things they might ask in an exam question. So these are really important points to know when revising required practicals. For each one, you'll see in the title, I have added a link to the video for the required practical. Highly recommend watching that, especially if you're a visual learner. So, absolutely essential. They also go through any additional things that I might have forgotten on this, but they do talk about the nitty-gritties of all the practicals. So really important to not only just listen to this, but also watch the videos. So the first one we're going to do is, I'll go over, is your force and extension required practical. So this is basically Hooke's law. It's for the forces topic and it is linked to Newton's laws. Okay. A typical question will be, start with the, oh, hang on, I've got my pen. Hold on. Get my pen going. I haven't got the ink ready yet. One particular question that they like to ask is defining what Hooke's law is. And it's all about the elasticity of an object or a spring. And it says here, when an elastic object, such as a spring, is stretched, the increased length is called its extension. Remember, it's the increased length. That's what sometimes some students can't or forget to work out, which we're going to talk about in the table here. So another little thing to look out for. The extension of an elastic object is directly proportional, another key word there, to the force applied to it. So they often ask you to describe the relationship between the force and the extension of the spring, and the words directly proportional are essential for that answer. Okay, obviously until you reach the limit of proportionality, but we'll come across that later. They've just given a list of general equipment because you could be asked to write the method for this practical. So just picture the equipment you need. This is a clamp stand. I'm not going to draw lines to it. So know your equipment. You don't often need a clamp stand, so that's important to use. These are your it's clamp stand, so there's clamps. We'll just call them clamps. Then you've got your spring. You will need a ruler. Why it's black, I don't know. But anyway, sometimes you will find which increases your accuracy of your measurement, because don't forget, there is a bit of error here. I don't know if you can remember doing this practical, but when you are hanging your, oh dear, that's a really bad drawing there. Hold on, I'm just going to erase that. That's terrible. It's doesn't supposed to look like that. But when you hook your weight on there, that's much better. It bounces a lot. Okay, and this is sometimes asked about. This is one improvement that you can make to help with the accuracy. And sometimes they attach or have attached a stick to the bottom of the spring, which helps you measure off a bit more precisely what the length is once you've added that weight. So don't be concerned if there is or isn't one there. It's just a little variation, but it could be something that they talk about that will help with accuracy. What else is there? I recommend with this one here to have a clamp on the table here, because health and safety issues, it will fall over once you start adding more weights on there. What else was there on there? I don't think that was, yeah, it's a splint and tape to act as a pointer. That's what I was just talking about. safety goggles in case it falls over and stabs you in the eye. Not a good option. So yeah, know the equipment here. There's not much to the method. It's literally add a mass and then measure where it's extended to. Done. Not a huge detailed method required here. But again, you will need to know dependent and independent. So your dependent is what you're measuring, and that's the extension of the spring. Independent is the mass that you are adding, typically 10 grams each time, which is equal to, also 10 grams, it's equal to 1 Newton. Okay. What are the control variables? Yeah, always use the same masses, same spring, because you could have a different spring constants on there, and same person taking the readings. Again, that eliminates the human error, or not eliminates, reduces human error. Okay. So you always must, when you're recording your results, do a 0 reading. So that's just basically the length of the spring or coiled up. Okay. And that's 2.5 here, centimeters. And the extension obviously 0 because there's nothing pulling it. Then when you add a mass, you then measure the length again. This time it's extended to 3 centimeters. So it's always the difference between the 0 reading and the length that it ends up as. Okay, so you must always subtract 2.5 from the extension to get your extension. Silly mistake. Lots of students have done it. Okay, so please be aware of that. What's this? Why is the top 0 of the ruler at the top of the spring? Oh, right, yes. So your ruler should be, can you see? Actually, there's one thing to sort of refer to. The top of the spring here should be at the 0 for the ruler. Okay, because yeah, the weight in newtons is 0. You need to measure that there. So obviously it goes 1, 2, 3, 4, etc. down that way. Okay, it's just easier to measure them around the other way. Otherwise you're counting down. Describe the purpose of the pin, as I said, to make it more accurate. Explain the results after. Right. So yeah, once you have calculated and you've done your extension, you graph it. You must always make sure this is on the Y and this is on the X, because obviously your independent is always your first column and it's always on the X axis. And what your results should show you is, hang on, it's right on here, directly proportional. Okay, and it's not very clear on this diagram, but sometimes it will just go all right and then suddenly curl up like that. Okay, when it starts to curl, that is your limit of proportionality. Where is it? Yeah, limit of proportionality, which I've written down here. Okay, that means that the spring will no longer return back to its original shape. It has lost its relationship between force. And quite often, this happens a lot when 30 children are doing this practical in the class. Yes, we stretch the spring until the spring no longer works. Always happens every time. So yes, explain the results after 6 newtons was added, and that's what it means. That's quite often the case with this. They will want you to identify where the limit of proportionality is. So you need to either read that off or remember what it's called, and describe the relationship between force and extension. It is directly proportional until it reaches its limit. Okay, but that is one of my favorite practicals. I like it. It's quite nice and simple. Yeah, and I just enjoy doing that one. One of my other favorite ones. It's not that boring. It's quite good fun and quite quick and easy to do. They've added another sort of slide here. I've kept it in just because you've got formulas on here just to remember, to remind you to use, how to rearrange, etc. They was dangling a horse on there and a decoration on there. it was just additional questions, but the question here, how could we measure the object's weights to show that our graph is accurate? Don't know if you know what a Newton meter is. We'd use a Newton meter to measure the weight of the two objects. So a Newton meter is like a scale, but again, it just measures in newtons rather than kilograms or grams. That's all. It was just something I just added in, but the main point of this slide here was to make sure you know your equations. Obviously, year 11s, you'll be given this, but year 9s and 10s, you need to learn them. But actually, this one here, you will be given in one on your worksheet, your equation worksheet, your extension. But remember the units, okay? Newtons per centimeters. So that's your spring constant. Okay, so therefore force will be newtons and extension will be centimeters. Okay, so yeah, make sure you know your units. Even if you're given all the equations, you still need to know the units. So I just need to sip of water, I'm struggling. Right, the second practical is about acceleration. Now this is Newton's, I said the first one's about Newton's law. No, this one's about Newton's laws. This is Newton's second law, sorry. And this is investigating the fact that force equals mass times acceleration. It's Newton's second law, okay? Second law states the acceleration of an object is proportional to the resultant force acting on the object and inversely proportional to the mass of the object. What's that saying is the heavier the object gets, if you apply the same force, the heavier the object is, the slower the acceleration. Okay. And if the mass stays the same, then the acceleration will increase if the force increases. Basically, it's a little bit of common sense. But these practicals here, again, I have a link for you to watch the practicals. It measures how force changes the acceleration, and this is number one, and then how mass changes. So they're looking at this statement here, they're comparing those. Okay, I'm just going to look here, describe some of the errors that could have occurred during this investigation, and how could we limit them. The measurements taken using a stopwatch, again, this allows a lot of inaccuracy with human error. What you could use and what is definitely preferable is using a light gate. Now, if you don't know what a light gate is, it's kind of, you can put it on the table and it has two light, or you can have one or two light gates, but the two light gates, you have a long ruler and you can have one light gate there, and in your truck, your car goes, oh, that's a really bad drawing. It goes through it and it measures how long it took that truck between the first and the second light gate. I'm just going to eliminate that drawing there because that is rather embarrassing, but it's a far more accurate way, and it's all computerized as well. It's a more accurate way of measuring time rather than a stopwatch, basically. So be aware of light gates and their benefits. So if we look at the first practical where we are looking at force and changing the force, remember the mass is always going to be the same for this. Okay, we're only changing one thing, which is this object here, the mass. Okay, what is a dependent variable? That's what we're measuring, and that's your time taken. What is the independent? And that's what we're changing, and that's your mass. What are the control variables? Yeah, same car, same surface as well, same pulley. Now, sometimes with this as well, especially with separates, they might mention friction, air resistance, and how to maybe counteract that. Okay, obviously when it's flat like this, you're going to get friction. So sometimes they raise up the platform, so it is at an angle, but not huge angle, but an angle that will increase it just to eliminate that friction force. So just be aware that that could be a possible question, and just so that you know that's the reason why, is just to eliminate the friction force. Okay, but yes, must use the same car because it must have the same mass, same surface, same pulley, everything. It's just the same. All you're doing is changing that mass. Okay. Describe the results of this investigation and how it relates to Newton's second law. So it's a quick statement. Reading your results, it says, as the mass or the force pulling the car increases, the acceleration of the car increases. Directly proportional. Again, it's that word. Or two words, sorry, not that word. There's two words there. Why is a pulley used instead of hanging the string over the table? Yeah, a pulley here, it makes it nice and smooth and less friction. Again, if you just had it dangling over the table, one, you'll probably wear out the rope, but two, it reduces that frictional force as well. Okay. The second one is, it's the same setup, but this time this is going to be your independent here. You're changing the mass changes, and this stays the same. So that's your force stays the same. And now you're going to be, oh, I can't read the bottom bit. Sorry, hold on. Mass of, now you're measuring the time taken of the car to travel the distance and mass of the car. Yeah, so you're just measuring the time again. Yeah. What is the independence mass of the car? Yeah, that's what you're changing. What are the control variables? So these ones just keeping the same. So the mass pulling the car. Oh, come on, pen. Thank you. Again, pulley and surface. It's exactly the same. And again, describe the results and how it links to Newton's second law. And you will state, as the mass of the car increases, its acceleration decreases. Again, because it's heavier. It takes a lot more effort to start the ball rolling, basically, or the wheels turning in this case. Okay, but again, watch the video, watch the practical in actually happening with a teacher, and that will also help you to remember. Waves, lovely, lovely waves. Yes, this practical always gives me a headache because you're trying to look at the waves and it does give you a headache. So what I have added and have included on here, hang on, bear with, hang on, is the method. There wasn't a method on here. I've added the method. It's important to know how all this apparatus is used, okay? What the method is, you're looking at the speed of the waves, okay? And to do that, you need to know this, this equation here. Speed of waves is your frequency times your wavelength. So what you're trying to measure here on this piece of paper underneath is the wavelength. And you do it by calculating, measuring 10 waves and then calculating the average, okay? So that's what the method is all about. So you've got to set it all up accordingly, adjust the height of the wooden rod. So this is a wooden rod which vibrates the water. Switch on the lamp and the motor and adjust the frequency. So that gives you the frequency you need for that equation. Freeze the wave pattern using a strobe. There are different ways of measuring that. If you try and measure these waves and the distance it covers, whilst it's still going on, that produces a headache and it's a nightmare. What you need to do, you need to either use a strobe so at the same frequency, so the waves actually look stationary, or you take a photo, okay? And from that photo, you can then measure. But typically the photo is a bit awkward because then it's not exactly the same distance. I preferably would say use a strobe light, and that will make the waves look stationary. Then all you've got to do is measure the distance of 10 waves and divide it by 10, and that will equal your average wavelength. Okay. List the equipment needed, that's all there. Elastic bands. What type of wave is shown in the diagrams? Know the difference between transverse and longitudinal, and know the examples of those, please. What is the dependent variable in this? That's your wave speed, that's what you're measuring. What is the independent? That's your frequency. You change the frequency and wavelength. So that's what you are changing. So obviously the wavelength obviously gets adjusted when you change the frequency. What are the control variables? Yep, amount of water, keep that the same. Color of the card. Okay, I'll go with that one. Same power pack, just keep everything the same, and just that's it really, basically. And then obviously you get your results, different frequencies. Here they've done the number of waves, but I suppose it depends on if the frequency is a lot lower, you are not going to get 10 waves within that paper size there. So they'll probably take an average of 3 rather than 10. So again, lower frequency, not so many waves over the duration of the paper. But obviously 3 is a minimum amount. Okay. What are the different parts of the transverse wave? Well, they've just added some extra bits here. This could be asked. Know what the amplitude is, and it's from the line of rest for the particles up to the peak of the well, just the peak, isn't it? And then all you could do, measure down to the trough. Wavelength is from the same part of the wave to the same part of the next wave. Doesn't matter where you measure it from. Frequencies and number here, so you've got 1, 2, 3. That's your, well, that's your 3 total wavelengths. Crest or trough, that's your crest, that's your trough. Okay. How accurate was this investigation, and what could have caused inaccurate results? It's all down to ruler measurements, human error. Yeah, just I don't think. I'm trying to think what else there might be. I don't think there is that much else really that could go wrong. It's quite a nice sort of straightforward one. I've added this, how to test the wave in a solid, because obviously this is liquid. It could come up, especially maybe for separates. This might be something additional, and you've got to be aware that you would use a oscilloscope, hammer hitting through the hammer, and it's how long it takes to get round, and then to the microphone. Okay, that's a typical practical, but what I will do, I'll probably look that further. There's not many questions on that, but just to be aware, we're looking at liquids here, but they could ask you about speed in a solid. Remember that sound travels faster in a solid because the particles are nearer to each other. I think that was it. That's all there is for the required practical. And I got this method here from BBC Bite Size. And they got quite a nice little page on there. Oh, I think I've got to sneeze. Oh dear. Right, again, next one about radiation and absorption. These are still all combined science required practicals. Okay, this is not separates yet. So radiation and absorption. We have, I don't know if you remember, it's a Leslie cube. Okay, so a Leslie cube, you would put hot water into the cube, and it will have different colors and different shades. You have matte and shiny, or white, copper, black, that sort of thing. So you've got different types of material on different sides of the cube. And you take your, here they call it in for a sensor or heat gun, and you measure the amount of heat coming off each side. The critical bit here is the distance must always be the same. Okay, all around the different sides, you must keep the sensor or the heat gun at the same distance when you're measuring. And then they are likely to ask you to plot. Don't forget, this is if it's a discontinuous bit of data, so actually maybe a gap between them. It doesn't really matter between the data. But yes, you can plot this as a bar chart. Okay. Let's look at the critical bit. So what is the meaning of absorption? It's the ability of a material to absorb a thing such as infrared radiation. Radiation is emitting. So these are the keywords here. So that's what you're measuring here, is how much heat or how much heat radiation is given off. Equipment, heat-proof mat, that will help any surfaces there. Heat-proof mat, obviously a kettle to boil the water, yeah. Different Leslie cubes, they have different colours. I mean, my one in my drawer has got copper on the side, so it really doesn't matter. But as long as you've got a shiny and matte and black and white and silver, you know, you've got variations there. And what they will generally ask is which surface has the best, is the highest for radiation. That means highest heat given off. And when you plot the results, the highest heat given off here is your matte black. That's the highest one. That means it doesn't keep. That means it will cool the fastest. It's losing the heat quickest. Whereas no, this one, sorry, matte white is the slowest, and therefore it will cool down the slowest. Okay, describe what infrared radiation is and some uses. So infrared radiation is a type of electromagnetic radiation. So an exam question may link this to your electromagnetic spectrum, which involves waves rather than particles. And know your examples where it's used. So a bit of a link there with your electromagnetic spectrum there. Always for each one of your on your spectrum, you need to know what it's used for, the energy involved, etc. Bit of a helpful hint for revision there. Why do we use heat-proof? Why do we use a heat-proof mat? Well, why do we think this? Because to prevent damage, okay, to the table, that is. What is a dependent variable? That's what we're measuring, so that's the amount of radiation. Independent, that's what you're changing, that's your surface area. Things that need to be controlled. Definitely the amount of water you put in there is got to be the same each time. And what I said before, the distance from the sensor to the cube, and you've got to use the same heat gun or radiation sensor. Okay, now that again is a nice little practical. I like that one. I like quite a few practicals, actually. They are good. Thermal insulation ones, yes, I like this one as well. This one's quite good as well. It's nice. There are different variations or different things you could try out with this one. You're basically measuring how quickly something cools down, and you're measuring or heat up, for example. This is your endo-exothermic investigation, finding out if something's exo or endo by measuring its temperature over time when you're adding different amounts of acid or alkali, whatever solutions you're adding, basically. Which direction does heat transfer? Describe what is meant by insulation. Yeah, I'll cut over these in a bit. In which direction does heat transfer? Always from high to low. What is the independent change in temperature? Independent variable in this investigation. Material use. Okay, for this one here, they're describing insulation. Okay, this method can be used to measure endo-exo, no problem. But they are specifically looking at thermal insulation here. So you can use this practical for other or use the basis for this for other investigations on EndoExo as well. So they will ask sometimes, why do you put card here? Why have we got 2 beakers, etc. So it's all to do with keeping the heat in and not letting the heat escape into the environment and mucking up our results, basically. Okay, you can then use different insulation material around the beaker as well. So the second beaker is 1, to stop any spillage, but 2, to enable you to then put some insulation around it. And it could be cardboard, it could be cotton wool, it could be cloth. That it's just depending on what material you use. Here they've used no insulation, sand, styrofoam and paper. Okay. What you're measuring is your change in temperature, and you'll do this over time, maybe here they've done every 3 minutes, measure the temperature, make sure it's the same person measuring it, again, avoids that human error, and just keep going. Make sure you time it for the same amount of time for each of them. I would also repeat at least 3 times maybe for each one to get an average. Something else to consider there. Yeah, what is meant by the term insulation? Insulation is it's how it prevents heat from transferring to the surroundings, whereas a conductor allows heat to go through it quite quickly and easily. A good conductor, that is. An insulator doesn't. Okay, it cannot absorb heat and therefore should retain it onto one's, stop it spreading through, basically. What was it? Is that the same? Okay, they put box in twice, but anyway. Which variables needed to be controlled? Yeah, same time. Same starting temperature. Always try and start the same temperature. Boil the kettle, stick it in. Obviously, be very careful, Bernie. Use the same beaker each time and the same cardboard, etc. And as I said before, the person reading the thermometer must stay the same. So these are some examples of the control variables. And then again, undoubtedly, they will ask you to plot your results as an opportunity for you to do a graph. This is obviously discontinuous data. This time they've done the right thing and put gaps between them, because of discontinuous data, you need these gaps. Whether it's continuous, you put them together. Material that insane and best and why. So plot the graph. So we've got here temperature change. So here the idea is that the more it's reduced in temperature, the worse it is. So we can say here no insulation is the worst, but the styrofoam is the best insulator because it only reduced by 14 degrees centigrade. Okay, so that'd be your evaluation. And then thickness, thermal insulation, thickness of insulation. So you can do, it's just a little variation of the practical basic. You can have just different thicknesses. I'm not going to go through. It's the same thing, just different question. Right, that's all the combined, I believe. Hang on. Yep, that is all the combined. So they're all the combined science required practicals. And the last one is on light. I do like this light one as well. I like it when refraction. Glass material. So let me just familiarize myself. So here, what is the difference between reflection and refraction? Really important definition there, or critical thing to remember. Reflection involves a change in direction of the wave when they bounce off a barrier. And this is for example, here, that's a reflection. Okay, always draw an arrow. Refraction involves a change in direction of the wave as they pass from one medium to another. So here, it changes, go away, thank you. Changes direction because your medium here is more dense. So the denser the material, the more, the greater the angle of change. Okay, hence why you can split white light. So that also depends on your wave frequency and wavelength. Okay, so that's the difference between reflection and refraction. The equipment you need for this is your ray box here, power supply, a slit, so it's like a little slidey thing, and if you look at it, it just has a little slit like that, so it only allows one straight line of beam of light through, which is handy. You will need ruler and protractor because you need to measure angles. Okay, that's really important. So in your exam, you must take a transparent ruler, sharp pencil, protractor, and calculator, obviously. Yeah, so what is meaning of N on the diagram? This is your normal line. So when you are measuring your angles, it's always against the normal line. So you can draw a dotted line through there. So when you shine a light through and it changes direction or reflects, it's your angle of incidence, angle of reflection, blah, blah, blah. And then here, this is your angle of refraction. Okay, so know where your angles are. Actually, I'm going to show here. So if you carry on there, that's your normal line, and it's always 45 degrees from the edge of the block or the line or the mirror, whatever you're using. Okay, so again, one angle, that's your incident angle. This is your reflected. These should be the same. Your incident angle should equal your reflected angle. Sorry, my nose is going. Your refracted ray, you work out the angle. So I'll do it from here. And then that's your angle of refraction. And that's pretty much all there are. So make sure you know where to measure the angle from, and it's always from the normal line. Okay, what should care be taken when using the ray box? It does get hot, the box gets hot. Okay, you keep that on for a while, it's not brilliant, so just turn it off between sessions. Sketch an image of the ray box you have used. Oh, I'm not going to write that. On the diagram below, use the terms to label the following. So yeah, that's what they've done there. Know those, very important. With this one here, sometimes they give you results and then you have to explain them. Other times they will have a diagram like this and they will expect you to be able to work out the angles. Okay, again, knowing where to measure the angles, that's the important thing. Each block and record the results. So you can do that on this PowerPoint. You can erase some of this. You can print this off or find some other exam questions and complete these 2, 3 examples here, okay, using a protractor. So practice using these, okay, and fill those in. Is there another method you could have used instead of a ray box to gain more accurate results? And why would this method not be appropriate? Could have used instead of a ray box. The only thing I can think of is a lamp. Maybe use a lamp. But if from the photosynthesis required practical, you know that a lamp will emit light like that, it won't spread out. You need a ray box to keep the light in a straight line. So that's anyway, I haven't really come across a question like that before, but describe what you noticed about the angle of reflection for both materials. That's your incident should equal your reflected. And describe what you noticed about the angle of refraction for both materials. That will be that your angles would be different. If you draw a line straight to there and you draw a line straight to there, if you compare this angle with this angle, this one, glass and perspex, this is more dense. So the, hang on, let me get my head around this. Yeah, so this one is more, glass is more dense, so the angle is more acute. Perspex, less dense, so there's less change in the angle of the light, basically. That's what you'll be needing to answer and evaluate. Okay, so the more dense, the less angle is done. Okay, I think that's about the light required practical. The only other thing they would mention, if I use this box here, is your light. So if we draw a line here, oh, that's really a bad line. When your light hits a different medium, like this, if you know about your white light and the different colors that make up the white light, you will notice that it will start to change like this, and then start to change again like this. So this is what's actually happening with your when your light beam with its width starts hits a different medium. Now, because white light is made up of multiple different colors, and they all have their own unique wavelength, this will cause different angles of refraction. So therefore you'll get different colors coming off, and you get your rainbow effect. So if you can't remember that, maybe add a little diagram on that. I might add a little diagram on that as well in here, just to show how refraction can be used to split light and why, basically, and it's all down to frequency or the wavelength of each color. Okay, that might also be asked in this sort of practical as well. Okay, apart from that, I think that's all the required practicals that you need to know about. Again, I've added a little link there as well to watch it. But that's about it, really. But if there are any more questions or any more queries, I will add some exam questions into the folder. Okay, I will find some and add some so you can at least practice them in your own time. But if there's any questions now, then I will take those, but I will stop recording first.